streaming analytics. We've been talking about in-memory computing yesterday and most of today. So in this talk, I'm going to focus on the processing and the analytics part of in-memory computing. So let me do the obligatory introductions. I'm representing a company called WSO2. We are an enabler for digital transformation. We're a 100% open source middleware company. We have offices in Mountain View, California, New York, London, Colombo, and Sao Paulo. 350 plus customers, 450 people in our organization, out of which 300 of them are engineers like myself. So before we get into streaming analytics, let me just take a moment to introduce the middleware platform that my company offers. We basically specialize in these 5 areas. We have a very strong API management offering. We are also in integration, identity and access management. Smart analytics is what I'm going to talk about today. And we also have a solution for Internet of Things. All right? So if you're interested in any of these other areas, you could have a chat with me after the talk. Okay. So let me introduce what we mean by smart analytics. Some of you may have heard the phrase "no man is an island," and we believe that this is relevant to streaming analytics as well. Streaming analytics should not be an island. It should not be limited to just compute or processing in a streaming fashion. The reason we say this is because our smart analytics offering is very highly focused on real-time analytics, so streaming analytics, but we also believe that it should be enriched with other analytics flavors, such as batch or predictive analytics, which can enrich the processing that happens in real time. So how it works is basically you have the streaming processing or the streaming analytics that processes in real time on streaming data, but you also enrich that by using aggregates or machine learning models that have been computed not in a streaming fashion. So you would have your aggregates that were computed in large batches, maybe coming in as a threshold on your streaming analytics platform. Or you might have run or trained a machine learning model, and you use the results of the machine learning model to make a decision in real time. So the idea is that you focus on streaming analytics because that is what makes sense for businesses. You need to make decisions in real time, but you don't limit it to real-time processing. You also enrich that with processing that is done not in real time. All right? So the idea is that you get data, you do the analytics, but that analytics is enriched by some inputs that are coming in from different flavors of analytics. All right. When we talk about streaming analytics, we mean complex event processing. So not just simple querying or simple filtering, but doing complex event processing. So how that works is basically the streaming analytics engine should be able to receive data from multiple sources, maybe in multiple formats, multiple protocols, combine these data, correlate them, identify patterns or trends within that, and then make a decision and send out that decision or communicate that decision to different devices using different protocols, right? So the type of processing that happens is similar to the example I've given at the bottom. We would do things like, okay, notify me if there's a 10% increase in overall trading activity and the average price of commodities has fallen by 2% in the last 4 hours. which means you are now creating or computing things which involves multiple streams, but it is also time bound, right? So you're giving a time bound and doing these computations within that time bound. Right. Okay, so I will be talking about different applications of streaming analytics in different industries. What I have listed out here are some of the industries and some of the most popular use cases that we have worked with our customer base. And I will, obviously I don't have enough time to go through each of them, but what I'll do is I'll concentrate on the ones that I have bolded out. So I'll take an example from the finance industry, particularly fraud detection. I'll take an example from retail in terms of recommendations, and I'll do also an example from smart energy. But if you're interested in any of these other types of application of streaming analytics in these other industries, you can definitely have a chat with me after the talk. All right. Okay. So I'm not going to go into detail about what fraud detection is and the history of it. I'm going to dive directly into the applications of streaming analytics within fraud detection. Now, when we work with our customers, some of the requirements they have multiple requirements in fraud detection. One of the things they want to do is they want to be able to, they have a lot of domain knowledge or domain expertise about what fraud means within their industry and their use case. So what they first want to do is to convert that domain knowledge into a real-time query, which can be detected in real time, right? So the first step is then to convert these domain knowledge into a complex event processing query, a CP query, right? So let's take a very simple, very basic example. If you take a credit card fraudster, he'd probably use, he definitely use a stolen card. Once he has access to a stolen card, he'd probably buy expensive stuff in large quantities very quickly. He might ship it to multiple places in order not to be tracked back to one location, etc. So the idea is, in streaming analytics, we should be able to write time contextual queries to capture these behaviors, which is different to the static queries that we would have had in the past. And I'll show you an example. So if we, for example, if we check against certain limits, certain upper limits or lower limits, previously we would have had limits defined somewhere, which a human being can go and change as and when the trends and seasonalities evolve. But how it differs in streaming analytics is that the human being doesn't get involved in changing those values. Those values are updated, the thresholds are updated by the analytics engine itself. So let's look at this query. What this does is it models a context-relevant normal behavior, and then it uses that context-relevant, the definition of that context-relevant normal to check against transactions coming in real time. So there are two queries. The first one is basically understanding what normal is at this point in time. So what we've done is we've taken the transaction stream and we've created a 60-minute time window. So a 1-hour time window. And within that time window, we calculate the average quantity and the standard deviation of the quantity bought for each item, and we store it in an in-memory table. All right, so this happens in real time. Every time you get a new event, you check for all the events within the hour, and then you update it. The second query is the one that detects fraud. Basically what that does is it takes the incoming stream, incoming event from the transaction stream, and it checks, and then if it is greater than that, we select that event and send it into a fraud stream. All right? So this is the kind of conversion of domain knowledge into streaming analytics queries that we're talking about. Just one more example to show you the different types of analytics you can do in a streaming fashion. Earlier we were doing a time window and creating aggregates and checking against it. What we're doing here is we're trying to identify a particular pattern in real time. So transaction velocity is basically the number of transactions you do within a certain unit of time, right? So if you have a higher transaction velocity than the normal for your card, then probably someone's got hold of your credentials and transacting on behalf of you. So how we do that is basically we write a pattern to capture that. Over here what we've done is, this is very easy, very simple, basic type of pattern, but it can be much more complex and much more interesting. We've taken E1 as the first event coming on the transaction stream, and then we're looking for a E2 event which follows that event where the card number is the same, all right? And then this 2 colon thing means, okay, you're looking for 2 or more transactions like that, 2 or more events to follow that first event, and we give it a time bound within 5 minutes. So you can also kind of vary these to put different types of filters within those events, which says, okay, the second transaction has to be larger than the first one, the third transaction has to be the average, or whatever. You can tune it the way you like. But basically the idea is that you are able to write queries which look out for definite patterns that domain experts know and want to detect. Envelope that with a time bound, and then you select interesting fields from any of those events and send it out into a fraud stream. So that's the detecting known types of frauds. So then what about, obviously, the unknown types of frauds? Because in fraud detection, half the battle is to keep up with the fraudsters who are evolving against anti-fraud measures, right? How that works in a streaming fashion is like what I explained at the beginning, where you would run machine learning algorithms on collected data, and you will then use the outputs of those machine learning algorithms in real time. So let's take an example from a clustering algorithm, right? What a clustering algorithm would do is it would take historical data and it would cluster those data into a k number of normal clusters, right? So all of the data that we have usually seen as normal will then belong to those clusters. Now, the output of that algorithm would be the locations of those cluster centers and a radius which defines the density of that cluster. So k number of cluster centers and k number of radius values. What we do in a streaming fashion is we take those cluster centers and radius into real-time computation, and when we get a transaction in real time, we try to see where does this fit in that picture, right? So I've just drawn this on an XY plane to make it very easy to understand, but usually you're talking about many more features than 2. So the event we got in real time does not belong to any of these clusters. They're away from the cluster center plus a radius. So then you identify that in real time by using the outputs of a machine learning algorithm, and you send out an alert for that. Right. Then the third type of fraud that customers want to detect are things much more complicated than what we've discussed, right? So what we discussed so far are point anomalies, basically individual transactions that are used to achieve some fraudulent means. But organized crime rings don't work that way. what they do is they come up with their fraudulent means, and then they distribute that among multiple transactions so that the fraudulent means is kind of simmered down, and individual transactions may look normal, but taken together as a sequence, they are very abnormal, right? So your machine learning algorithm which does point anomalies, or your fraud rules that you've written to detect point anomalies don't work for that case. So how we use streaming analytics to kind of attack that is we basically do Markov modeling. So how Markov modeling? So Markov models are basically mathematical representation of a randomly changing system, right? So what we do is we take historical data, historical transactions, and we look at certain characteristics, so certain features of that transaction. So for example, the price or the quantity traded, or the frequency in which it has traded, etc. And we attach different classes or different states for each of those transactions. So some of the transactions will be low valued, low quantity transactions, some of them will be low valued, high quantity transactions, etc. So if I take this example, this picture as an example, so there are 5 states, A, B, C, D, E. Okay, there's no D. A, B, C, E, F. Okay, and we classify each transaction as a particular type, and then we count the number of times a transaction of type A was followed by a transaction of type C, right? And in doing that, you can count the probabilities of A being followed by C as opposed to A being followed by B. So by doing this, we create a transition of a probability matrix, right, one time, and then in real time, when we get more and more transactions, we are able to then classify them in real time and update this Markov model. So how we detect fraud or fraudulent transaction sequences is when we receive a transaction sequence that has a combined probability which is lower than our threshold, we identify each of those transactions in that sequence as set of transactions done to achieve a fraudulent means, and we send out alerts for each of those transactions. All right. So that's the application of streaming analytics and its different constructs in fraud detection. Right. So I'm now going to go into the next use case. But if you have any questions for this use case, it might be a good time to ask questions now, because when I go to the next one, you might forget. Okay, because that one's going to have different constructs and different things. If you have no questions, that means I've confused you enough that you don't want to ask questions. All right. Okay. Oh, I didn't want to go there. I wanted to ask you what you, the first picture that came into your mind it's too late. So when we say retail recommendations, usually what's the first thing that comes to, forget that picture, right? What's the first thing that came to your mind before you saw that picture? Was it that picture?
Yeah.
Of course, right? So why am I talking about this? Everybody knows this. This is all news. Why? Why am I talking about this in this conference? Well, I'm not going to talk about this, right? What I'm going to talk about is beyond this. This is only a small part of the type of recommendations that we have offered in our recommendation solution. So when you go to Amazon, eBay, whatever, what you usually get is, okay, you're buying a camera. Okay, these are the other things that other people bought along with this particular camera, right? But what we can do using streaming analytics is much more than that. So the idea is that we are able to build a digital shopping list for our customers using different angles of recommendations. Now, the recommendation that you saw before which was the Amazon tab thing, is basically based on the product. So you're buying a product A. What are the other things that go hand in hand with this product? You would know that by looking at your previous orders where customers have bought other things with this product, so correlations between this product. Or if you do some analysis across transactions, you might be able to see correlations of customers buying certain products a little later. So people bought a camera, and then 1 month down the line they decided, okay, I need to have a case because this is always, it's not, I need to protect it or whatever, so they buy a camera. But similarly, you can also look at other angles, and we've done that for some of our customers. You can look at the customer's buying history. So we were providing this recommendation system for, I can't say their name, but one of the largest wholesale food distributors in the US. You do the math. So in their scenario, they had regular customers who were buying regular items in different frequencies. So some would buy a consignment of wine on like every Friday. Some would buy something pudding or whatever, something else on the last Tuesday of the month. Some would buy something on the 30th of every month, etc. Right? So the idea there was, along with products that go with other products, we should also recommend things that the customer regularly buys but has forgotten to add that today. Right? So we were looking at regular items that the customer bought in different frequencies. Where's my stopwatch? Average order value, well, I'll come to that. Then the third aspect that we looked at, actually there are 4 aspects, I bunched 3 and 4 together, were seasonal purchases. So obviously during Christmas time you would buy festive things, you'd buy mulled wine or Christmas pudding or I don't know, whatever. Easter eggs during Easter, umbrellas during the rainy season, etc. So if there are current trends in your retail store or your e-commerce portal, then you want to add a recommendation or two with regards to that as well. Then the fourth kind are the unlikely pairs. So these are the pairs that you would find by doing much more analysis, maybe running a machine learning model, which is not apparent at the first look of things, but which become apparent through analysis of data. So I'm talking about things like beers and diapers, right? Beers. Do you guys know about the beers and diapers thing? No? Okay. So in 1998, I think, way before streaming analytics, this supermarket, so data warehouses were like the in thing back then, right? It's really cool to have a data warehouse. So they put all their transactions into the data warehouse, they did some data mining and figured out that beers and diapers had an uncanny correlation, right? So this is a supermarket. So what they did is, they didn't know what it meant. What they did is they put the beers and the diapers together in the store, right? And then the sales just went off the roof. And then I suppose they just waited until someone came and bought the two together and then asked them, why are you buying the two together? I don't know how they did it, but what they figured out is that new parents or new dads would do a late night trip to the supermarket to buy Pampers or diapers, and then figure out it's going to be a long night, let me have a couple of beers as well, right? So it might sound, it might sound a bit unbelievable, but trust me, it's true. I had my first baby last year, and my husband and I, our relationship with beer has only grown since then, okay? So it's true. So that's a fourth kind of thing you want to recommend. Things that are usually not, very apparent to you, but with your analysis, data analysis, you know, okay, these two things also go together. You want to give all those recommendations. Right, now let me tell you about average order value, order percentage, and granularity. Okay, let me start with granularity. Now, when you are doing when you are analyzing these kind of things, you need to, or your customer, the retail store needs to be able to calculate them for a granularity that makes sense for them. For some, it will be per week, for some it will be per month, per day, per hour, and for some it will be a combination of things, right? These products calculate for an hour, these products calculate for a month, etc. Order percentage. Now, when you are doing these recommendations, obviously there will be certain products that go very well together, or there will be certain products that a customer always buys, as opposed to some that he buys some of the time, right? So you need to calculate the order percentage. So for example, you take a customer's last 10 orders and you see what are the items that were there, or each time. So that will have 100% order percentage, and there might be customers who don't have something like that. But for each item, you calculate, okay, out of the last 10 times, this appeared 8 times, meaning the order percentage is 80%. And when you recommend, you will then recommend the highest first, obviously, and give lower priority to products which have lower order percentage. Then lastly, the average order value is important because now we're trying to recommend based on various angles, right? So we are obviously going to get a lot of different recommendations. If you give all these recommendations to the guy, if you give him 10 things, he's just not going to look at any of them, right? So you want to give him stuff that is reasonable enough for him to purchase. So how we attack that is basically we calculated the average order value for a customer, and we recommended products up to a multiplier of that average value. So if for example, if a customer would spend $100 on average, we would recommend up to $120 or $150, and the retail store or the e-commerce portal will define what that multiplier is. Okay. So how does that look? Let's say the current order has products. I was doing these slides and I just couldn't think of products. I spaced out, so I just put A, B, C, D, E. How original. So the current order has A, D, L. So what happens is then we look, okay, so these are the things that the customer wants to check out today. We then take, when we receive the order, we then check for recommendations for that customer based on the customer's buying history, products buying history, and other trends. We have the order percentages, and then we prioritize that. So basically, most retail stores want to prioritize it so that the customer's buying history is given first priority. Because if the customer has bought this before, then there's a high possibility that he would want to buy that thing before he buys something else that is recommended to him. But this can be customized. So you prioritize it first by the different type of recommendation, and then by the order percentage, and then you cap it using the average order value, a multiplier of that average order value. So let's look at how the implementation basically looks like. You get the order checkout stream, right? So when a customer wants to check out, you get that event. So that event has those three events, 3 products, A, D, and L. You join that with in-memory table. So the recommendations per customer, per product, etc., can be calculated offline. Can be, once again, this is why I said other flavors of analytics enrich the streaming analytics process. So you can have them in a database, but you bring them into an in-memory storage So you have them in in-memory tables so that you can join them in real time, and then you join any recommendations. So basically any items that are not in that original event, you join in sequence. So join customer stuff, you join recommendations based on the product, you join based on trends. And then finally, you get the recommendation stream, which is all the products, and then you can do another filter in there, which leaves out any products that go beyond the order value, etc. Okay, so I've also added some queries to show how this looks like in a query format, and I've only put in the joining part, right? So you get the order checkout stream, so that's the order checkout event, and you join that with a customer history table, and even within the table or within the stream, if you want, you can add a filter, right? So you don't just read everything from the table, or you don't take every event from the stream, you take only certain events and certain items or certain rows from the event, from the table. So you add a filter. So over here I've said I only want to get any products that have an order percentage of less than 70. And then obviously, I need to join it based on a common thing, so customer ID. And then I select all those, all the items that come in the event, as well as everything that, all the recommendations I get from the table, and I insert it into a temporary stream. And then that temporary stream, I join with the next table. All right? And so I can do this as many times as I want. And then finally, I send all of those things into a recommendation stream, which I will use to filter further and send out the recommendations to the customer. Now, in our experience, I mean, it looks like a lot of work, and it looks like a lot of sequential processing, but this happens in less than 1 millisecond, right? In some of the implementations we've done for our customers, it happens in less than actually 0.5 milliseconds, so it's nothing really. Customers, usually I think the visual reaction time is 20 milliseconds, and this happens in less than 1. Yes?
I have a question.
Yeah.
Is there any kind of feedback loop involved in the sense that you track the impact your recommendations have on the individual customer?
Yeah, there is, definitely. So actually that's a good question. It works for both use cases, the recommendations as well as the fraud detection. But that feedback, so you capture that. So you give, okay, let's take the recommendations example. So you give the guy 3 recommendations, and he selects 2. And then you can do this for everyone, right? And you capture the ones that were taken, and you capture the ones that were left, and then you send it back into your data dump, right? And that feedback then is calculated again offline. It doesn't have to be in real time. So you send that back to your processing engine, which analyzes the trends, and then it will deprioritize that. Maybe it'll change the value that I said as order percentage. That could be also a value that says, okay, this is not a very good recommendation. And that can also be done for different groups. Now, you might be recommending the same thing to, high net worth guys as well as low net worth guys. But if an item is working well for group A and not for group B, then you do it that way as well. Yeah.
Yeah, a question about filtering data, compression of data for this streaming. Do you have something like what do you do actually with incomplete data or old data which is not quite valid for current realization and so on?
Okay, so basically you're talking about cleaning the data, right?
Compression.
Yeah. So in terms of streaming analytics, you can't really, you have, so when we take stream processing, we specify the event type, right? So this event should have these fields, and these fields should be in these formats. So every event that you get should conform to that. If there are, let's say for example, if there are null values, right? You can, what you can do is you can front the streaming engine with processor to kind of insert like basically default values to that, and that's how you would do that. But if you're basically taking decisions based on a certain field, so let's say price, and your incoming event does not have a price, and we inject 0 as the price, then that event is not going to be any use, right? You're not going to be able to make a decision based on that event. So incoming, if you're doing streaming analytics, you need to make sure that your events are properly populated before it. But for, in terms of using it for the batch analytics, which then adds value to the streaming processing, there basically you can do any amount of data cleaning because it's offline, right? So you clean the data and then you add that back. Now that actually reminds me to talk about something about the Markov modeling, right? Now I mentioned we take a large amount of data. So let's say we are going into this new sequence-based fraud detection thing today, and we need to create a transition matrix, a probability matrix. So we take all transactions from the beginning of time up till now, we clean it, make sure only the good ones are in there, and then we create the probability matrix, right? When we get new orders or new transactions, we, in real time, we update the probability matrix, right? So as we go, if the patterns are changing, if the seasonalities are changing, then the probabilities will change with them, right? If sequence A to B was previously low, the probability was low, and if there is now a propensity for A to be always followed by B, it will then automatically become high, and the other probabilities will go down. So in that way, you actually, I mean, as you get the data, your models correct themselves in a streaming fashion anyway. Does that answer your question? Okay. Any other questions? Please? No, okay. So we move on to the last use case, which is smart energy. So what makes energy smart is actually the analytics, right? What else could make it smart, right? So in this space of doing energy analytics, we are able to do, we are able to get a holistic view of the aspects of energy by listening in to the different types of data that is available to us, right? First of all, we have the production, the energy production data that is generated by the manufacturer. So any sensors that are attached to the equipment, the power lines, etc., the amounts of power generated, etc. And then we have, on the other side, we have the consumer data. So I'm talking about like smart meters, which generate data like a couple of times a minute, or couple of times a minute, and basically understand, okay, how the consumption works. And then there is obviously the weather data, right? So the solar flux, wind speed, humidity, etc. So you'll see that these two things, production and the consumption, are two-way arrows, because you get the data into your analytics platform and you can provide some feedback to the energy companies and the consumers as to how to manufacture and how to consume. But you can't really send any feedback to God, right? Say, okay, rain less. So it's a one-way arrow. Okay. So the application of streaming analytics in the energy area is based on different things. One, so I'm going to talk about three different aspects: production, consumption, and resilience, like recovering from faults, etc. Right? So when you talk about production, you can optimize it based on different things. You can optimize it based on demand, right? So in the past, energy companies didn't have data about consumption every minute, right? They would have data for maybe a week or a month. At the best, they'll have for a day. But now, with the smart meters that are installed, they have data about, or they have access to data about how energy is consumed within the day, within the hour, within the minute, in different households, in different groups of households, etc. Right? So they have a very good idea, but exactly how and very accurately how energy is consumed. So back in the day, you would just manufacture chunks of energy, right? You produce. If your supply is greater than the demand, you waste the energy because you can't store it. And if your supply is not meeting the demand, then some of the consumers will have a blackout. So how that differs in the current day with the use of streaming analytics is basically you stream the usage, so the data that is coming off of the smart meters, to calculate the total demand for a given period of time. I'll go through this query, bear with me. So you get the demand stream. So you have to do a little small transformation to just get the readings and then transform that into an actual demand value, right? And then you can see how this demand varies within a day, within the hour, during the summer, during the spring, whatever. And based on that, you produce intelligently. Now, so we get these events from smart meters every minute, right? I think twice a minute or whatever. So now, in order to understand this, or in order to aggregate this, it's a bit of work, right? You need to aggregate per minute, per hour, per week, per day, per week, etc., to understand, okay, how does this change. But it's very easy using streaming analytics. This query, one query, will do that aggregation in any granularity that you prefer. So if you take a look at it, what we're doing is we're defining an aggregation from that first stream of data, usage stream. We group the aggregation per house, right? And you can do it per anything really. And we calculate the average power used. And we aggregate it by the timestamp that we receive the data for every minute, hour, day, month. So we just specify that, and we just plunk this query on that stream, and it creates for you a comprehensive set of aggregates to the minute, to the hour, to the day, to the month, right? So once this is done, if you say, give me the average power consumption of house number 24 between 8:13 p.m. and 9:42 p.m. or from January 1st, 12:15 a.m. to January 20th, this time, it will calculate that based on these aggregates and give you sliced and diced in the ways that you want. Right? So this is very important and useful for energy companies to be able to, they receive the data, but how do they really know what the demand is if they can't aggregate it smartly? This is how you do it. The other aspect is how you optimize your production based on the weather, right? Previously it was based on the demand, now it is based on the weather. So you also have all these sensors that give you weather data, right? And what you can do is then, by reading those data, you understand what are the what are the energy sources that are going to be available for your production in what proportions, right? So if it's a very sunny day, if it's a very still sunny day, you'd probably do more solar power production than thermal or wind, right? So you transform that transform the weather data into the availability of energy sources, and you basically break down your production based on those available energy sources, and you cater that to the demand. So that is where now you're joining multiple streams. So you're combining streams to gain insights that will help your production. So you'll get the weather data and you'll understand the energy source availability, and then you split the production to those different energy sources based on the demand, right? And you produce intelligently. Smart, okay, so that's production. Now consumption. How this helps consumers is basically, okay, so now they have these smart meters, they're emitting their power consumption every minute, so they need to get something back from this, right? So what the energy companies, and one of the energy companies that we are working with does is that they provide a service to their customers, and now, let me go a step back, right? Now, these different energy sources create power in different ways, and these the power is cleared at different prices. If it is renewable energy, it's cheaper. If it is non-renewable energy, it's more expensive. Based on the demand in the day, the price differs. So the clearing price also differs at different times of the day. So what these guys do is they send information about how the price is going to deviate within the day tomorrow, based on what the data they've received about demand and whether the energy source availability, and they send it out to the customer. So what the consumer does is then it looks for cheaper times to run some of the utilities that can be scheduled. For example, your laundry or charging your electric vehicle, you can schedule it for a time where the clearing price of energy is lower. And if you're a household who is also able to produce energy, if you have solar panels, for example, on your roof, you can then use the weather data or the energy source availability data that is provided by your your energy company to produce data for your usage, as well as provide energy back into the grid if you have excess. So this basically, the streaming analytics part is not done by the consumer, it's done by the energy company, but it is provided as a service to the consumer so that the consumers will stick to that energy company and benefit. And then the final aspect for smart energy is basically how you make the power system more resilient. So if you just Google this, the Northeast blackout of 2003, it was a software failure actually, which which originated this, but it just affected a very small area and number of people, but it wasn't handled in time, so it just expanded into this completely large blackout, which affected 45 million people in the United States, in 8 states of the United States, and another 10 million people in Canada, right, so in the Northeast. So the idea is to now use the millions of sensors we have on everything to prevent this before it goes into a blackout. So this would mean getting information from equipment as well as power lines. So let me show you how the streaming analytics plays in this scenario. So you will get sensor events from your sensors from the equipment as well as the power lines. So the idea is to identify outages and failures and transmit that data, and then you join the failures with the demand, with your demand stream, so you know, okay, in the next hour I need to provide this amount of energy, and these are my lines that are currently failing, so how do I use the rest of the network that is working well to load balance to meet that demand, right? So you can't just blindly change your mechanisms of your grid without having an idea about your demand. It needs to cater to the demand. So you combine streams and then you solve the problem. So I've just used this a different type of query here. So in that fraud detection example, you saw a pattern where we had one event followed by another event, and I had put an arrow there. In this one, I have something similar but something slightly different. From every E1 event, which has a state of faulty, which comes to the status stream, comma, followed by another event, which has the same state. So basically the comma indicates in this language, in this real-time streaming query language, the comma indicates subsequent events. Whereas the previous example, there could be other events in the middle, but you're looking for a pattern among a large set of data. So you can do it both ways. If you're looking for a pattern which comprises of events just after the other, you use this pattern. But if you're looking for other patterns where some other events may have happened in the middle, you could use a previous construct. So I'm looking for multiple events that have a faulty state, and I'm sending an alert to the failure stream so that some corrective measures could take place. How am I on time? I'm good on time. So the resulting streams can then be used with the grid controller to notify outages. And so these outages can also be notified to the consumers early on, before the outage happens, so that the consumers can bring down their consumption until things are patched back. So basically, those are the three use cases that I wanted to cover. I didn't want to cover too many use cases because I wanted to go into detail so that you understand what are the different types of analytics constructs that can be used for different use cases. So obviously, we use these interchangeably in different use cases. If you want to have an idea about what we do at WSO2, you can go to our website. If you are interested more about analytics, you can go to the Smart Analytics page. And if you want to know more about the individual solutions we have for different industries, you can go and check the solutions out. So just a disclaimer that we also have this analytics server. The base thing is also a 100% open source product, so you can download it from our website and you can use it. We have, I would like to say, we have comprehensive documentation. You probably can decide whether it's comprehensive or not. And we have lots of samples, etc. So try it out, download it, try it out. The query language that I used is very similar to SQL. That's it. I am obligated to also tell you by my marketing team that we also have a conference coming up in November in London. So, and we will have track on analytics as well. So if you're interested, you can join. Very sorry about the marketing, but I'm obligated to do that. All right, so if you have any further questions, be pleased to answer them. Or if you want to have a longer conversation, we can have a chat afterwards. Come on. No questions? All right. Thank you very much.